Before we conclude in this course, it's important to note a few things about transmission lines. Although we've covered many mathematical equations throughout this course, it's crucial to understand the physical significance behind them. The characteristic impedance of an ideal infinite lossless line is Z0, which is a real number. The distributed circuit model of a line shows that wave propagation depends on the charging of a series of inductors and capacitors by a signal source. The real value characteristic impedance signifies propagation along the line. This is because it is as if there is a resistance on the right side of the line that is continuously receiving the transmitted energy. If the line is finite in length, and we connect a resistor RL at the end that exactly matches the line impedance Z0, it results in an impedance-matched condition. This is an ideal scenario because the signal is fooled into believing that there is a continuous path for it to pass energy through without any energy loss in the middle. This creates a perfect deception tactic where the signal does not encounter any reflections or signal loss. In the case of a short terminated line, there is no voltage at the terminal, which also means that there is no voltage at the output endpoint because it is directly grounded. The voltage wave is shorted when it hits the endpoint. Since the voltage at the endpoint is zero, the reflected and incident voltages at this point must also be zero when combined. This means that the refraction coefficient gamma 0 at this endpoint will be -1, which indicates that the refracted voltage wave must be inverted to be combined with the incident voltage wave to achieve a total voltage of 0. When the line is ended to an open circuit, there is no current flowing at the end, and the reflected voltage wave will be equal to the incident voltage wave at the end. This means that the refraction coefficient gamma 0 at this endpoint will be 1. In addition, since there is no current flowing at the end, this means that when a current wave reaches the end and hits the open circuit, it is reflected back as an inverted current. This reflected current wave is necessary to combine with the incident current wave to produce a total current of 0 at this endpoint. When a finite length line is connected to any impedance ZL, there will be some reflections, and the incident and reflected waves will interfere with each other, creating a standing wave on the line. The standing wave results in the input impedance changing with the position. Now we know that the reflection is the reason for the transmission line effect, which allows the line to convert impedance. When we are drawing lines on a printed circuit board, we may come across different line widths, and their widths are directly related to the characteristic impedance. In general, a wider line width results in a lower line impedance, while a narrower line width results in a higher line impedance. If there is a discontinuity in the line width, it means that there is also a discontinuity in the impedance, which leads to the reflection phenomenon. We can use the miter taps to alleviate the reflection. Another common case of reflection is a right angle band. In this case, we can use the swept band or miter band to reduce the reflection. Okay, in the next video, we are going to touch the ending of this course.